Yeah. All right, so we did an example in the previous lecture, and I talked about calculating the electric field. I talked about how you determine what your source charges are, how you determine what your distances are. In fact, went through most of this little laundry list of variables from the expression for calculating the electric field. I want to do another example for you. This time, again, we'll have 2-point charges as our source charges, but this time they won't be close to each other, and we will have to treat their distances more carefully. But before we do, I said at the end of the last one that I would briefly talk about the units that we got for the electric field, which remember was newtons per coulomb. And I said that that made sense, and here it is. It derives actually from Coulomb's law, which is what this is here. And simple enough, Coulomb's law is the force on a test charge is gotten by multiplying that test charge by the electric field of the source charge, which we calculated earlier. But I also said in deriving the expression for the electric field in the first place that the electric field was related to the electric force by I came up with this expression. I said, okay, F is equal to Q times, and I didn't actually write E. I had that big long expression with the summation and all that. And then I said, okay, if I simply divide both sides by Q, that gave me the electric field. And so there you are. There are the units, because the units of force, of course, are newtons. Units of the test charge, units of all charge, is coulomb, so newtons per coulomb. So that's where it comes from mathematically. Physically, the meaning of the units, newtons per coulomb, is this is what an electric field does to a test charge. It applies a force on the test charge, but how big that force is going to be will depend on how big the test charge happens to be. For the same electric field, if I put a test charge in that field that's twice as big as another one, then that bigger charge will experience twice as big a force. Okay, but it's the same electric field. So the electric field applies a certain amount of force per coulomb of charge, a certain number of newtons of force per coulomb of charge for coulomb of test charge that you put in the field. So one more time in English, the electric field, the way you think about it, the way you interpret it, is that it is a phenomenon that applies a certain number of newtons on a certain number of coulombs of test charge. And the electric field is created by the source charges and only by the source charges. Okay, so that's the significance and meaning of the units. Right. So now for my next example, again, we'll have 2 charges. And this time, the charges will be of opposite sign, or these are source charges now. So the problem at hand, pardon me, is to calculate the electric field near a dipole, specifically. Calculate. Calculate the electric field for dipole made up of two charges, plus or minus 1.5 nanocoulombs at a distance of 0.012 meters from the positive charge. The charges themselves are also that distance apart. And point P is collinear with them. And this description of the problem that you can see on the board now is the entire reason that the first thing you do is make a drawing, because who the heck can make sense out of that? Well, theoretically I can, and by the time I'm done with you, so can you. But, well, anyway. Okay, so we've got a dipole. Remember a dipole. A dipole is 2 point charges, typically. In fact, almost universally. A dipole is 2 point charges of equal magnitudes but opposite sign of charge, separated by some typically small distance. Okay? By small, I mean the distance between the two charges is usually small compared to how far away from the dipole you are where you want to calculate the field. In this case, that's not true. In fact, the distance the distance where you want to calculate the field is actually equal to the distance that the two charges are from each other. But whatever, it doesn't matter. We can still calculate it. All right, and anyway, so the point P, remember P represents the point in space where we want to calculate the field. That point is actually collinear with the axis of the dipole. What's the axis of the dipole? Well, you got two charges, and so the axis is this imaginary line joining the positive and negative charges. Okay, so what that all boils down to is, and I didn't say this, and I'm tired of writing, so I'll just put it here. It's the point P is located at 0.12 meters from the positive charges, from the positive charge. It is therefore 0.024 meters from the negative charge. In other words, what we have, step 1, draw a diagram. We have a negative charge on the left. We have a positive charge on the right. And we have our point P at a distance that's the same as how far apart they are from each other. Yeah. They are distance d apart, and as it happens, that's also d. Doesn't have to be, that's just a coincidence of this particular problem. Okay, cool. We're not done with the diagram, but hopefully we got that much understood. All right, the next thing I want to do for my diagram is to draw in the total electric field at the point P. You remember in a previous recording I had I had like 7 source charges and 1 test charge, and then I drew a whole bunch of electric field vectors at the location where the test charge happened to be. Okay, same idea here. Only now there is no test charge in sight. All we've got are source charges. So at the point P, the electric field from the positive charge is going to point radially away from the positive charge. First of all, it points away from positive charges. Field lines point away from positive charges and toward negative charges. So at the point P, the field of the positive charge is going to point away, directly away from the positive charge. Label that E plus temporarily, just to see it. As for the field of the negative charge, it also will point radially away from the negative charge. Only, I'm sorry, not radially away. Not radially away. I taught you earlier. Field lines for negative charges point toward the negative charge. Now, by the way, so far I haven't given you any reason for these choices of directions. I just told you what they are and said, suck it up. In the next recording, I will talk about the reason for these directions. Okay. But for now, so the electric field at the point P, due to the negative charge, is going to point directly toward the negative charge. But as far as the magnitude of the field, which amounts to, as far as the length of the arrow that I need to draw for the negative electric field vector, it's going to be smaller than the field vector of the positive charge. Okay? Because the negative source charge is farther from point P than the positive charge is. And very important concept here, the length of this vector, no matter what I drew, yeah, I did okay. The length of the negative field vector is not going to be half the length of the positive field vector. Okay? You might think, but why not? The distance that point P is from the negative charge is exactly double the distance from the positive charge. So since you double the distance, shouldn't you half the field? The answer is no, because remember, the electric field goes like Q over R squared, right? So if you double the distance between your source charge and your point P, if you double the distance, you decrease the electric field by a factor of 4, 2 squared, right? So this red arrow should be just 1/4 the length of my blue arrow. And that wasn't too bad. I'm close enough that I won't worry about it. So you can see here that means that the net electric field at the point P is going to still point away. It's going to still point to the right there. Okay, cool. So I think that's pretty much our diagram. Step 2, impose a coordinate system on this whole thing. Choose anything you like. Almost anything would make sense. I'm going to call this the Z direction. The Z direction. Why the Z direction? I have reasons. And we'll call that the Y direction. So that means the X direction is pointing out of the board. Why am I doing such a weird choice? Because it'll be useful in days to come. Okay. And of course, it doesn't really matter. So it's a matter of labeling. All right. So there's that. So it's our coordinate system. And now finally, 3, solve the problem. Okay. Unlike the previous example, this one, we are definitely going to have 2 terms with 2 different distances in our calculation of the total electric field. That is to say, the total electric field is going to be E plus E minus, and we've got to be careful to take into account the correct directions. Okay. For the positive charge, that's going to be K times Q positive over, let's see, the distance that the positive charge is from the point P is that distance D there, D squared. And that's pointing, we've already decided that that field points in the positive Y direction, so we'll call that J hat, okay? And as for the E minus, we've already established that's going to point in the minus direction, so I'm going to go ahead and put the minus sign there. K, Q minus over, now the distance that the negative charge is from the point P is D plus D, 2D, and that has got to be squared. And that is a really common source of error. You've got to square the 2 as well as the D, so don't miss that. Okay, and negative charge there, and that's again in the horizontal direction, which I've defined to be the Y direction. Okay, So K. And so now I plug things in. So K again is 8.99 times 10 to the 9th Newton meters squared over Coulomb squared. Q positive is 1.5 times 10 to the, say it's nanocoulombs, so 10 to the minus 9th coulombs. D is, what did I say, 0.012? 0.012 meters squared. Okay, and that's in the j hat direction, sorry. Yeah. Minus, same thing, 8 point, running off the screen here, 8.99. Now, if you're mathematically inclined, you can do factoring and various other clever things to shorten this up, but whatever. 910 Newton meters squared, Coulomb squared, 1.5 times 10 to the minus 9th coulombs over, oh, wait a minute. This is a negative charge. Why am I putting in a positive number? I should put a negative number, shouldn't I? No. No, no, no. Again, no. Maybe I said this with forces. I probably did. If I did, this is a great time to remind you. If I didn't, this is a good time to say it. When you're substituting in values for negative charges, never ever substitute in the negative number, because the negative number goes to telling you the direction that the vector, in this case the electric field vector points. Okay, but we've already dealt with that. We figured that out at the first step of the problem, practically, what direction these vectors would point. So we've already got the direction. If you were to put in a negative sign here, you would reverse the sign of that, and you'd end up having both forces pointing in the positive direction, which is, of course, incorrect. So when you're substituting in numbers, for negative charges, never include the negative sign of the charge. Just put in the magnitude of it. Okay? And so then 2 times 0.012 meters, all that, quantity squared, and that's also in the j hat direction. And I plug in the numbers, and I got 7.0 times 10 to the 4th newtons per coulomb. You should check this, make sure you agree that the units cancel out to be newtons per coulomb. Check my math, make sure I got that correctly. But that's the thing. And so the important takeaways from this particular example, the crucial importance of drawing your picture, especially including the field vectors, so that you get the directions correct. The second takeaway is make sure you get these directions and make sure you get these numbers correct, especially squaring these distances. There's a lot of places where you can go wrong here, and it's not difficult to go wrong, but it's not difficult to go right either if you're just careful. Okay? So there's that. And then, yeah, so those are the crucial ideas. And so there's that. And so for my third and final example, I'm going to go into 2 dimensions and show you things can get a little more complicated, but I will reassure you this. Practically nothing that I'm going to do in the upcoming example will be new to you. It's just a new application of an old idea. Okay. Next recording, please.